In this video, we will learn that how to create parsing tree and write derivation of a given input string if we are provided a parsing table. So the first question you should ask that what kind of parsing table we are provided. This parsing table is same for a collection of bottom-up parsers. If we have SLR parser, which is simple LR parser, then we can use the same parsing table for that parser and the same parsing algorithm that we will see here. Similarly, if we have look ahead LR parser, then that parser also use the same parsing table. And if we have canonical LR parser, then we will also use the same parsing table. So in this video we will learn that given parsing table of any of those algorithms, which is this one, and a context-free grammar and an input string, how to create parse tree and how to write a derivation. That will be rightmost derivation. There are 4 different operations corresponding to LR parsing. The first operation is shift operation, which is represented by this S in the parsing table. In the shift operation, we take an input and we push it onto the stack. Also, we add a state onto the stack. So, if we have shift 3, then we will push third state of automata onto the stack, and also the current input symbol will also be placed onto the stack. Second operation is reduce operation. And the reduce operation is represented by R in the parsing table. In the reduce operation, we take the top of the stack and replace it by the left-hand side of a projection. For example, if the stack has CC at its top and the action we have to perform is R1, then it implies that we have to replace this CC with the left-hand side of projection 1, which is S. So we'll remove CC from the stack and replace it with S. So this is our reduce operation, and we will see it in action soon, so don't worry about it at this moment. Number third operation is acceptance of the input string. And when we are performing our parsing and we reach to this cell of the parse table, then this A represents the acceptance of our input string. Number fourth action is error. If during our parsing we reach to any of those empty cells, then it is a parsing error or a syntax error, and our string is not part of our programming language. Don't worry if you still have some confusion about these actions, because we're going to do an example and everything will be clear to you. So let me clear the board and then we will start with our example. Our board is clear and we can start with the parsing algorithm. This parsing algorithm is used by a bunch of bottom-up parsers or a bunch of LR parsers. These are the data structures used by our parsing algorithm. Our parsing algorithm will use a state stack which will have states of DFA on it. Our parsing algorithm will also use a symbol stack which will have terminals and non-terminals on it. we will have an input buffer, and we will also have different kinds of actions. We could have shift action, reduce action, accept action, and error action. These are the 4 actions. Initially, our state stack will have starting state 0 on it. Our symbol stack will be empty. Our input buffer will have complete input, that means C, C, D, D, followed by the end of input marker, which is $sign on it. Now we can start our algorithm. We will see what is on the top of our state stack, which will be the rightmost state. In this case, we have 0 on the top of our stack, and then we will see what is our current input, and which is C. Then when we are at state 0 and our input symbol is C, then we will perform action shift 3. So I will write here action shift 3 that we have to perform in the next step. So let me also write different steps. This is my step number 1, this is 2, 3, 4, and so on. So I have to perform shift 3 in my next step. The shift operation implies that first on my state stack I have to add third state of automata, and shift operation also shift the input symbol, which is we are currently looking at, onto the symbol stack. So my input buffer will have now C, D, D left on it. So we will continue our algorithm. We will match state 3 with input symbol C, and once again we have to perform operation shift 3 in the next step. So we once again add R3 on the top of our stack, and once again we move this C to the symbol stack. So we will have here CC, and we will have DD left on our input buffer. Then we will match this 3 on the top of our stack with next input, which is D. And then we have to perform shift 4 operation based upon our parsing table. That means our stack will have now 4 on top of it, and we will also move this D to the symbol stack because it is a shift operation, and our input buffer will have now D and $sign left on it. And now we have to see what will be the next action. To that end, we see that on state 4 and input symbol D, we have to perform reduce 3. Now this 3 does not represent state of the stack. Instead, this 3 represents projection number 3. That means this projection. So we will write here reduce C goes to D. Now please look at the reduce operation carefully because this is different as compared to the shift operation. So here we will have our reduce operation. First of all, we will remove this D and replace it with the left hand side of the projection, which is C. My symbol stack will now have small c, and capital C on it. My input buffer will remain the same in case of reduce operation. It changes when I perform shift operation, but in case of reduce operation, we don't make any change in the input buffer. Now we have to carefully see what operation we have to perform on our state stack, because we have replaced one symbol Therefore, first we will pop one state. If we have replaced 3 symbols, then we have to pop 3 states from our state stack. But in this case, we have replaced 1 symbol, so we have to pop 1 state. And next, because we have replaced D with this capital C, so in this case, we have to see the go-to part of our parsing table, that at state 3 and grammar symbol C, we go to state 8. So this is the reduce operation. When we are at state 8 and we see the input symbol D, then the operation we have to perform is reduce 2. So I will write here reduce, and instead of 2 I have to write second projection, which is capital C goes to small c and capital C. Now we have to look carefully that how to perform this reduce operation. First of all, because I have to remove 2 symbols from the top of my stack and replace them with 1 symbol. So let's do that. So I remove 2 symbols from top of my stack and replace it by 1 symbol. I have removed the right hand side of this projection and replace it with the left hand side. This is the reduction operation. And because I have removed 2 symbols, so I will remove 3 and 8, 2 states. I will write here 0, 3, and I will remove these 3 and 8 because I have removed 2 symbols from top of my stack. And then I have to add another state here based upon this C. And to that end, I must look at the go-to part. So at state 3 and grammar symbol C, I have to go to state 8. I will write here 8. And that's my reduce operation. So we continue. In case of reduce operation, my input buffer remains the same. So when I'm at state 8 and see the input D, then I do reduce 2. That means I have to do reduce 2, which is replace small c and capital C with a capital C. So let's perform this operation. I will remove these 2 symbols. That means I will remove these 2 states. So here I will be left with only 1 state. And these 2 symbols will be replaced by this C. So I will write here C. And because I've written here C, so I have to add another state here. And for that end, I have to see the go-to part. On 0, on grammar symbol C, I go to state 2. So I have to write here 2. And my input buffer will remain the same. And we continue and see the next section. On state 2 and on input D, I do shift 7. Shift 7. And in the shift operation, first I will add state 7 here, and also I will move this D to my symbol stack. Now my input buffer has only $sign left on it. Now at state 7 on $sign, I do reduce 3. So I have to write here reduce, but this 3 represents third projection, which is C goes to D. So I will take this D out and I will replace it with a capital C. So now my stack has 2 capital C on it, and because I've taken a D out, which is a 1 input symbol, so I will take 7 out also. I will have here 0 and 2. And because I have added a C on the stack, therefore I have to see that where to go from state 2 on symbol C. My answer is 5. So I will write here 5. My input buffer remains the same because I have done the reduce operation. Now I will continue from 5 and on input $5 input $, we will do reduce 1. So we have to do here reduce 1, where 1 is projection S goes to capital C and capital C. So I will pop both of those C's from the stack and replace them with capital S. And because I have popped 2 C's, therefore I also have to pop 2 states. So my state stack will have only 0 left on it. But because I have added S, so I have to see what to add here. So on 0 and symbol S, we go to state 1. I will add 1 here. And we have a $sign here. Once again, we look at our table. We are at state 1 and we see input $sign. Then our action is accept. So we write here accept because we have accepted our input. That means that our input was part of our programming language. We have no syntax error. But now we have to make parsing tree using this table. To that end, we only have to look at the reduce operations. That means this operation, this operation, this operation, this operation, and this operation. Because it is bottom-up parsing, so we will start from our input and we will go towards the start symbol. So our input was C, C, D, D. And we have to see those reduce operations. The first reduce operation is this one. And when we're creating the parse tree, always have to consider leftmost symbols. So in this case, it says that replace the leftmost D with this capital D. So this is the D that I have to replace. I replace this D with a capital C. I'm done with this reduce. Now I have to perform this reduce operation. This reduce operation says that take the leftmost small c and capital C and replace it with a capital C. So the leftmost small c is this and the leftmost capital C is this. So I have to replace them with capital C. And next reduce operation is this one. And it says that take the leftmost small c and capital C. So leftmost small c is this one and the leftmost capital C is this one, and I have to replace them with a capital C. And the next operation is that it says take the leftmost D and replace it with a capital C. So this is the D which is not consumed yet, and I replace this with a capital C. The next operation is that take the leftmost CC and replace it with S. So these are the two leftmost CCs and I replace them with S. And that's my parse tree. We could also write the derivation of our input string, but that will be the rightmost derivation, because in bottom-up parsing we have rightmost derivations. To write derivations, we once again can use those reduce instructions. But in this case, we will start from the start state, that means we will start from the last reduce instruction and then we'll proceed towards the first reduce instruction. So our last instruction is that replace S with two capital C's. So I write here C and C. Now we are done with this reduce action. Then our next reduce action is that replace the rightmost C with D. So I will replace the rightmost C with D. So my next derivation will be CD. I'm done with this reduce action. My next reduce action is that replace capital C, the rightmost capital C, with small c and capital C. So this is my rightmost capital C. I have to replace this with small c and capital C. I'm done with this reduce action. My next reduce action says that place capital C with small c and capital C. So I will place this capital C also with small c and capital C. I'm done with this reduce action. My next reduce action is that replace capital C with small d. So my next derivation will be that I will replace this C with D. And that's it. I have started from my start symbol of context-free grammar and I'm successfully able to drive towards the input. And this was my rightmost derivation. So that's it for this video. I hope that you will be able to now create parse tree for any LR parsing algorithm. That's it for this video. See you next time. Bye.